Today we're going to explore an article that just came out that could be a fascinating breakthrough in artificial intelligence called the Hierarchical Reasoning Model, or HRM. I'll link the PDF to the original article below so you can read it yourself. Now, the article suggests that there's a new approach that achieves superior reasoning capabilities with just a fraction of the resources. In the next 35 to 45 minutes, we'll explore how HRM's brain-inspired architecture achieves remarkable efficiency. Now, my name is Vernon Neal Reed, and my background is in networking and cloud infrastructure, and I'm going to relate it to that. I use Manus AI with this, and it helps me learn and understand deeper. And it also allows me to share with you as I grow in the AI infrastructure space. By the end of this presentation, you'll understand why HRM's architectural approach could transform how we deploy AI in general, and also specifically in network and cloud environments. And we will also discuss the practical implications for network and cloud infrastructure. So let's begin by understanding the reasoning challenge that current AI systems face. So let's start by understanding the fundamental challenge. While today's large language models are impressive, they face significant limitations when it comes to complex reasoning tasks. As you can see below me in the diagrams below me, traditional LLMs and HRM take fundamentally different approaches. First, there's the scaling issue. The industry has been following a bigger is better type approach, right? GPT-4 has over 1 trillion parameters, but we're seeing diminishing returns. So simply adding more parameters doesn't proportionally improve reasoning ability. Think about how we approach network scaling problems. We don't just add more of the same components. We redesign the architecture for efficiency. That's exactly what HRM does for AI reasoning. The computational inefficiency is particularly relevant to you as cloud engineers. Traditional LLMs require massive GPU clusters, significant memory, and enormous energy consumption, all translating to higher cost and environmental impact. But perhaps most importantly, traditional LLMs lack hierarchical processing. It's like having a network without distinct control and data planes. Everything happens in a single layer, making multi-step reasoning inefficient. As a research paper notes, reasoning remains a critical challenge in AI. It's not just about pattern recognition. It's about devising and executing complex, goal-oriented sequences, something our human brains do naturally through hierarchical processing. So how does HRM address these challenges? Let's take a look. So what exactly is the hierarchical reasoning model? At its core, HRM is a novel AI architecture inspired by how our brains process information hierarchically. As you can see in this diagram, HRM features a dual module architecture. Unlike traditional LLMs that process everything through a single pathway, HRM separates processing into 2 specialized modules with bidirectional information flow between them. This design isn't arbitrary. It's inspired by how our brains work. Our prefrontal cortex, right? This one here, handles abstract planning and strategic thinking, while other regions manage detailed execution. HRM mimics this natural division of labor. But what's truly revolutionary is the efficiency. While models like GPT-4 require billions or even trillions of parameters, HRM achieves comparable or superior reasoning with just 27 million parameters. That's over 99.9%. Again, that's a reduction of over 99 99.9%. And even more impressive is the training efficiency. Traditional LLMs need massive datasets, often billions of examples. HRM achieves it with just 1,000 training samples. This isn't just an incremental improvement, it's a paradigm shift. For you as network and cloud engineers, this means AI systems that could potentially run on much smaller infrastructure. It can consume far less power and cost a fraction to operate, all while delivering superior reasoning capabilities. Let's dive deeper into how this dual module architecture actually works. Let's examine HRM's architecture in more detail. As you can see, HRM consists of two specialized modules working in harmony, the H module and the L module. The H module, or hierarchical module, functions like we said before, the prefrontal cortex in our brain. It handles abstract planning, strategic decision making, and maintains the broader context of the reasoning task. It operates at a slower timescale, focusing on the big picture rather than minute details. If you think about your network architecture, the H model is analogous to your control plane. It makes high-level decisions about how traffic should flow without handling the actual packet forwarding. The L module, or local module, is responsible for detailed computation and tactical execution. It implements the strategy determined by the H module, handling specific calculations and focused execution. It operates at a faster timescale, dealing with immediate tasks. This is similar to your network's data plane. It efficiently executes the forwarding decisions made by the control plane, processing individual packets according to the established rules. What makes this architecture powerful is the bidirectional information flow between the modules. The H module guides the L module's execution, while the L module provides feedback that informs the H module's planning. This creates a continuous feedback loop that enables complex reasoning. This architecture might sound familiar to you as network engineers. So next, we're going to explore that analogy more explicitly. One of the most powerful ways to understand something is through analogies and concepts you work with every day. And in this case with HRM, it was very helpful and somewhat easy to compare this with network and cloud engineering. The parallels are striking and not coincidental. As you can see in this diagram, HRM's architecture mirrors the control plane data plane separation that is fundamental to modern networking. The H module, like your control plane, orchestrates high-level decisions and strategic planning. The L module, like your data plane, handles the detailed execution and tactical processing. Looking at this comparison table, you can see how closely these concepts align. Just as your control plane manages routing decisions without handling actual packets, the H module manages abstract planning without executing detailed computations. And just as your data plane efficiently forwards packets based on routing tables, the L module executes detailed computations based on the H module's guidance. This is also similar to the philosophy behind software-defined networking, which is separating the control logic from the execution hardware creates more efficient, flexible systems. HRM applies this same principle to AI reasoning. The hierarchical processing in HRM is also reminiscent of network protocol layers. Each layer handles a specific level of abstraction, from application level down to physical transmission, with well-defined interfaces between them. So now that we understand the architecture, let's look at the remarkable efficiency advantages this design enables. Now let's talk numbers. The efficiency advantages of HRM aren't just incremental, they're transformative. As this chart dramatically illustrates, we're looking at orders of magnitude improvement in key metrics. First, parameter count. Traditional LLMs like GPT-4 have around 1 trillion parameters. HRM achieves superior reasoning capabilities with just 27 million parameters. That's not a typo, it's a reduction of over 99.997%. Imagine the memory footprint difference. Even more impressive is the training data efficiency. While models like GPT-4 require billions of training examples, HRM needs only 1,000 samples to achieve its performance. This isn't just more efficient, it fundamentally changes what's possible with limited data. For cloud infrastructure, these efficiencies translate directly to bottom line benefits. Let me highlight a few implications. Dramatically reduced compute requirements mean lower hardware costs. Smaller memory footprint means more instances per server. Reduced training and inference costs mean more economical AI services. Perhaps most exciting for network engineers is the possibility of edge deployment. With such a small footprint, HRM could potentially run on edge devices or smaller network appliances, bringing advanced reasoning capabilities closer to where data is generated. And all this efficiency doesn't come at the cost of capability. HRM maintains deep reasoning capabilities through its architectural innovation rather than brute force scaling. But where did this architectural innovation come from? Let's look at the brain-inspired design principles behind HRM. HRM's revolutionary efficiency doesn't come from nowhere. It's inspired by how our brains process information. Despite consuming only about 20 watts of power, the human brain remains the most efficient reasoning system we know. As you can see in this diagram, HRM's architecture maps to specific brain regions. The H module corresponds to functions of the prefrontal cortex, the part of our brain responsible for planning, strategic thinking, and high-level decision-making. The L module corresponds more to regions like the motor cortex that handle detailed execution and tactical operations. One key principle borrowed from the brain is hierarchical processing. Our brains don't process everything at the same level. They maintain multiple levels of abstraction working in concert. This allows for more natural problem decomposition and more efficient resource allocation. Another critical brain-inspired feature is temporal separation. Different modules in HRM operate at different timescales, just like different brain regions. The H module processes information more slowly, but with broader context, while the L module operates more quickly on immediate tasks. This is similar to how you might design cloud microservices, some handling long-running processes and others optimized for quick responses, all working together as a system. These brain-inspired principles aren't just theoretical. They deliver real-world performance. Let's look at how HRM performs on benchmark tests. Theory is important, but results matter. Let's look at how HRM performs on 3 challenging benchmark tasks that specifically test reasoning capabilities. First is ARC-AGI, the abstraction and reasoning corpus. This benchmark tests a model's ability to discover patterns and apply them to new situations, essentially testing abstract reasoning. These are tasks that even the largest LLMs struggle with, yet HRM performs exceptionally well despite its much smaller size. Next is Sudoku Extreme, which tests logical reasoning and constraint satisfaction. These aren't just any Sudoku puzzles. They're specifically designed to be challenging, requiring multi-step logical deduction. HRM's hierarchical approach allows it to maintain multiple constraints simultaneously while exploring solution paths. The third benchmark is maze hard, testing spatial reasoning and pathfinding. These complex mazes require planning several steps ahead while avoiding dead ends. Exactly the kind of task where HRM's H module can develop a high-level strategy while the L module handles specific navigation steps. What's remarkable in this chart isn't just that HRM performs well, is that it matches or exceeds models like GPT-4 and Claude that have over 40,000 times more parameters. This demonstrates conclusively that architectural innovation can be more important than scale. These impressive results have direct implications for network and cloud environments. Let's explore some specific applications. Let's bring this back to your world. How might HRM's capabilities transform network and cloud operations? This diagram highlights 4 key application areas where HRM can make an immediate impact. First, network intelligence. Imagine having advanced reasoning capabilities directly in your network management systems, optimizing traffic routing in real time based on complex, changing conditions. Unlike traditional AI approaches that might require sending data to massive cloud-based models, HRM could potentially run directly on network devices, providing intelligent optimization with minimal overhead. For cloud environments, HRM could revolutionize resource management. Its ability to reason through complex constraints makes it ideal for dynamic scaling and workload optimization across distributed systems. And because it's so efficient, the cost of running the AI itself becomes negligible compared to the savings it generates. The edge computing implications are particularly exciting. With HRM's small footprint, you could deploy advanced reasoning capabilities directly on edge devices, enabling smart decisions to happen where the data is generated, reducing latency and bandwidth requirements. Finally, security operations. HRM's reasoning capabilities could transform threat detection and response, identifying complex attack patterns and orchestrating automated responses. Its efficiency means you could deploy this intelligence throughout your security infrastructure without massive overhead. The common thread across all these applications is that HRM enables AI reasoning in environments where traditional LLMs would be impractical due to their resource requirements. Okay, let's wrap up by summarizing what we've learned and discussing next steps. As we wrap up, let's recap the key takeaways about the hierarchical reasoning model. First, HRM represents a fundamental paradigm shift in AI architecture, moving from brute force scaling to intelligent design inspired by the brain's hierarchical processing. The efficiency numbers bear repeating. 27 million parameters versus billions or even trillions, and only 1,000 training samples versus millions or billions. This isn't just an incremental improvement. It's a revolutionary approach that could change how we think about deploying AI in network and cloud environments. And crucially, this efficiency doesn't come at the cost of performance. As we saw in the benchmark results, HRM outperforms much larger models on complex reasoning tasks, demonstrating that architectural innovation can be more important than scale. For those interested in exploring further, I've listed some resources here. The original paper provides all the technical details, and there is an open source implementation available on GitHub. As network and cloud engineers, I encourage you to consider the implications for your infrastructure. How might these efficiency gains transform your AI deployments? Could you enable new capabilities at the edge? Would your security operations benefit from embedded reasoning capabilities? HRM shows us that the future of AI isn't necessarily about building bigger models. It's about building smarter ones. And that's a future that aligns perfectly with the efficiency and performance goals we all share as engineers. Let me know what you think about all of this in the comments.